Okay, my name is Yuxin Miao. A brief background, I got my PhD in 2005 from the same department, focusing on soil science and precision agriculture. After that, I did 2 years postdoc and then went back to China to work at China Agricultural University for about 11 years. And then in the end of 2017, I moved back to Minnesota. Because of the time, I need to be brief because I don't have much time left.
I'm sorry.
So I should go first, have gone first. But I will talk about improving decision-making in precision nitrogen management of corn using remote sensing and machine learning. Precision agriculture, many people have heard of this, but you may wonder, what's precision agriculture? In 2019, International Society of Precision Agriculture organized 50 scientists around the world to come up with a kind of official definition. And the definition is precision agriculture is a management strategy that gathers, processes, and analyzes temporal, spatial, and individual data and combines it with other information to support management decisions according to estimated variability for improved resource use efficiency, productivity, quality, profitability, and sustainability of agricultural production. And we know crop growth, yield, and quality is influenced by many factors, including genetics, the varieties we select, and also environmental variables like weather conditions, and also soil landscape conditions, and also weeds and disease and pests, and also many management factors. And the challenge is that genetics, environment, and management factors, they interact with each other. And if we think about these interactions and in the context of precision agriculture, it's more challenging because we have spatial and temporal variability associated with genetics, environmental factors, and management practices. So for the past 30 years, a lot of progress has been made. A lot of sensing technologies have been developed, and we can collect all kinds of data. Right now, many farmers are confused with this data. They don't know how to use this data to improve their management. Because right now, people still use some traditional statistical methods to analyze the data and just not enough. So there's a need to use some new analysis methods like artificial intelligence or machine learning models to analyze the data, to extract more information to improve the decision-making. So I will use precision nitrogen management as a case study to see how machine learning models can improve the decision-makings. So for precision nitrogen management, we aim to match nitrogen supply with crop nitrogen requirement in total rate. And also in space. At the same time, we need to consider the spatial, the temporal variability. Year to year, weather differences result in different nitrogen requirements in different years. And also within one growing season, the crop nitrogen need is not the same. Early during the growing season, the crops are small, they don't need much nitrogen. But if we apply them before planting, if we have heavy rainfall, then a lot of the nitrogen can get lost. So we need to optimize all this together. So we are developing an integrated approach to precision nitrogen management. And we can first divide a field into management zones. Each zone is relatively uniform. And then we can adjust the nitrogen rates in different zones based on experiences. And also we can use machine learning models to estimate the optimal nitrogen rates. And right now we are also using crop growth models to do long-term simulations to determine the optimal nitrogen rate in different zones. And then we can apply about 30% of the total rate before planting, because we don't want to apply all the nitrogen before planting to reduce the chance of losses. And then during the growing season, we can use crop sensing technology to do diagnosis and to determine how much nitrogen will be needed at different parts of the field. And then use that to guide in-season nitrogen management. And these sensors can be installed on variable rate fertilizer applicators to do on-the-go sensing and variable rate application. In addition to crop sensing, crop sensors, we can also use UAV remote sensing and satellite remote sensing to diagnose crop nitrogen status and make nitrogen recommendations, and to create a nitrogen prescription map and use this to guide variable rate application. And this way we can improve nitrogen use efficiency and the profitability, and also can contribute to climate change adaptation and mitigation, and also reduce nitrate leaching. So because of time, I will focus on proximal and remote sensing based in-season site-specific nitrogen management. And different sensing technologies have been used to diagnose crop nitrogen status and make in-season recommendations. So the idea is we can start from kind of a regional optimum nitrogen rate, like IMRTN. Then we can apply a small portion of that before planting. And then during the growing season, we can use these sensors to do diagnosis. You are deficient, or you have optimal nitrogen status, or you have surplus. And this information can help us to adjust how much site-dress nitrogen will be applied. And this will guide site-dress nitrogen rate adjustment. The green seeker sensor is most commonly used. It has two spectral bands and calculate NDVI and RVI. And so this has been used to predict the nitrogen status indicators and agronomic variables like biomass, nitrogen concentration, nitrogen uptake, and nitrogen nutrition index. And we can see is okay, but has a lot of room for improvement. The R square is less than 0.6. So one way to improve this is to use some sensors with more bands, like crop circle sensor has 3 bands, including a red edge band. And using new sensors, we can improve the predictions. For biomass, doesn't really increase, but for other variables, we can see some improvement in the predictions of these variables. But still not ideal, right? Still less than 0.7 DR square. Still has room to improve. Now, in the past, people only use sensor data to do the predictions. And now, I think we need to incorporate other variables in the prediction, not only just use sensor data. And we can do this using machine learning models to incorporate more variables. For example, we used random forest regression to include sensor data, the nitrogen rate information, the soil organic matter information, and the planting density, the growing degree days, accumulated precipitation, and also Shannon diversity index. That's an index to reflect rainfall distribution. And now we can see we still use the green seeker sensor, but we significantly improved the prediction. The R square all above 0.8. And if we use this approach, even we use the better sensor, the result is similar. That means when we include more variables using machine learning, we can narrow the difference between different sensing technologies. They perform similarly because other variables contribute a lot to the predictions. And we can see the nitrogen status diagnosis accuracy was increased to 86%, and the kappa statistics was quite high, 0.62. So that's based on limited sites. So how about expanding this kind of concept to larger regions? So we used a large data set, included 49 site years of data involving 16 nitrogen treatments and 8 states in the Midwest. And we also use machine learning models to incorporate genetics, like different hybrid variables, and also weather data, environment. We want to be practical, so we just used soil texture information, and also the sensor data, rapid scan, 3-band, and also management information, including whether it's irrigated, whether it's tilled, and what's the previous crop, whether it's soybean or legume or non-legume crops, and seeding rate, and also pre-plant nitrogen rate. And we can see the R's, even with this diverse data set, large data set across 8 states, it performed very well using the machine learning based approach, almost above 0.8, and especially for the plant nitrogen concentration, that has been very difficult to predict. But in this research, we found the R square is above 0.9, so that's very impressive or very significant improvement. And we can also see the importance of different variables, and the NDRE, that right age different, the normalized difference right age index, was the most important variable for all the 4 variable nitrogen indicators. And for nitrogen uptake and NNI, it seems other variables are not very important. But for biomass and the nitrogen concentration, you see, in addition to the sensor index, several other variables are also very important. So that means including other variables is really necessary to improve the predictions. And this machine learning methods can not only be used to improve nitrogen status prediction, we can also use this to make nitrogen recommendations. So this is a data set involving 12 site years of corn nitrogen rate experiments, including different nitrogen rates, different soil types, different seeding rates, and 6 years. So we used 2014 to 2017 data to establish a machine learning model to predict yield using soil sensor data and weather data and management data. And once the model is established, we use some new data to test it, to validate it, and then also to see how we can use that to make in-season nitrogen recommendations. So when we have this model established, we can simulate, to predict, vary the site-dress nitrogen rate, and then use that to predict yield. So then we can determine which nitrogen rate will optimize yield. So this is the prediction. So simple ratio, simple regression means we just use the sensor data, NDVI or RVI. The R square is 0.6, around 0.6. And then we use lasso regression, including more variables. The R square increased 0.76. And then we use random forest regression. The R square was improved to 0.79. And then we use the model to simulate the side-dress rate that will optimize crop yield and to determine which side-dress rate should be applied. So we can use this to make in-season recommendations. So not only determine the optimal nitrogen rate to optimize yield, we can also include nitrogen price and corn price information to determine the nitrogen rate that will optimize marginal economic returns. So we compared with the measured optimal side-dress nitrogen rate, and we can see the relative error is about 14 to 15%. In addition to this, we have also developed a calibration strip and remote sensing based nitrogen recommendation method. So this is based on the ramp calibration strip based approach developed or proposed by Oklahoma State University. So in this approach, they apply a series of nitrogen reads to a crop field. And then during the growing season, before side dressing or top dressing, you can just visually observe the crop growth in this field to see how the crop growth is at different nitrogen rates. So when you increase the nitrogen rate, then you will see no difference between two nitrogen rates. And then that will be the optimal nitrogen rate. So they use that information to adjust how much side dress or top dress will be needed. In addition to visual observation, you can also use a sensor to collect sensor data to see how the sensor data change with the nitrogen rate. And then, here the nitrogen, the sensor data, green seeker sensor data, NDVI, increase with nitrogen rate and then reach a plateau. So that's the optimal nitrogen rate. So this approach works pretty well if your field is small, or if your field is quite uniform, right? Because this just have one calibration strip, ramp calibration, one side of calibration for the whole field, to use this to guide the management in the whole field. But in large fields, it's not uniform. So there's an argument where to put the calibration strips. Depending on the location, different nitrogen rates will be recommended. So this is not enough to have one or two in a large field. So based on this idea, we developed this new recommendation method. So we just have 5 or 6 nitrogen rates, and we apply them in strips across the whole field and replicate that several times according to the size of the field. And then we delineate the strips into grids. Each grid will be a management unit. And then during the growing season, we use satellite remote sensing to monitor the crop growth conditions and calculate NDVI for the whole field. So the 5 or 6 grids next to each other, covering different nitrogen rates, form one block. We call it block or transect. So for each block, we can, before side dressing, we can see the response curve of NDVI. So NDVI increase with nitrogen rate and then reach a plateau. So that area is the optimal nitrogen rate. So when we know this, then we can determine the block specific optimal nitrogen rate. So this is the total nitrogen rate. Then we know how much is applied before planting. So the optimal nitrogen rate minus the nitrogen rate applied before planting will be the nitrogen rate to be applied at side dress time. So based on this idea, we can create the side dress nitrogen recommendation map, and then use this to guide in-season variable rate application. So this approach has several innovations because we use year, site, and hybrid specific calibration information to make the recommendations. In the past, we conduct some experiments somewhere and then use that information to guide farmers to improve their management. And many farmers say, that's too far from me. I want something close to my farm. Now we are using your own field, to this information to help you to make recommendations. And also, every year, you are not using the results from previous years. You are using current year's information. And also, hybrid can change. They keep changing the varieties to be planted. So we are using the current variety or hybrid you are using for this field. So this is provided the most accurate information for the farmers to make decisions. And we are using high spatial and temporal resolution planiscope satellite remote sensing images. This has daily revisit time and has 3-meter resolution, good enough for this purpose. So this is more practical than current proximal sensor-based strategies for wide applications, because this has global coverage, because sensors, many places people just don't have the sensors, right? So this, you don't need to have sensors to use this technology. And also we are using a planiscope satellite, but this technology is compatible with other satellite or aerial or UAV remote sensing images. So if you don't have the satellites, you have UAV images, we can also use that. But also if you have planes and to fly, then that's also fine. So this can be implemented in any farmer's field directly without the need of previous data accumulations. So in the past, in order to develop the algorithms, you need many years of data or many years of data to develop a model and then try to apply that. But if you apply that in an area not included in the model development, it may not work very well, but this doesn't need that. And also, farmers don't need to purchase any new equipment, such as new sensors, as long as they have access to the variable rate applicators. Many farmers have these applicators, so they don't need to purchase any new equipment. But we also found this approach still has some room for improvement. We assume one block is uniform, but one strip is 70 or 80 feet wide, and you have 5 or 6 strips. Well, that's a large area, and we do have variability there. So this is an example. So this different nitrogen reads. Each strip has different nitrogen read. And then this is the NDVI map on June 17th. And we can see the NDVI patterns doesn't really match the nitrogen strips. That means nitrogen is not the only variable influencing the spatial patterns. So soil landscape conditions also influence this. So we need to consider the soil landscape properties in the decision making. So we are developing a new recommendation method using machine learning models by incorporating soil landscape information, historical yield information. So some places may have historically low yielding potential, and some have high yielding potential. We need to know that information. Also, pre-plant nitrogen reads and remote sensing data. So we can try to optimize the nitrogen read in each grid by considering all these soil landscape conditions and historical yield information. So this is an example of in different grids, the optimal nitrogen read in different grids. So all these technologies are being tested by conducting on-farm trials. This year, we will conduct 10 on-farm trials in Minnesota, and also about 10 trials in Indiana. So in summary, precision agriculture is information intensive, and a large amount of data has been collected, but most farmers are overwhelmed and have not benefited from the big data. And AI has a great potential to improve decision-making in precision agriculture, and more close cooperation between precision agriculture scientists and AI experts is needed to further improve applications of AI in precision agriculture. Right now, we just use some simple machine learning models. Of course, there are many more advanced methods that can be used to improve precision agriculture decisions. And the combination of proximal or remote sensing data with genetic, environmental, and management information using machine learning models can improve corn nitrogen status diagnosis and in-season site-specific nitrogen management. And right now, we are also trying to integrate precision nitrogen management with variable rate irrigation by working with WASU, and also trying to also incorporate cover crops to see altogether how we can reduce nitrogen leaching and improve the nitrogen use efficiency. And I would like to acknowledge the support from Pioneer Regional Nitrogen Team by allowing me to use their large data site, and also our students and researchers, postdocs in my lab, and also the funding from Sino Green, AFRIC, and NRCIS, and also Minnesota Robotics Institute. Thank you for your attention. Any questions? Yes.
The planet scope image, is that free or how much?
Yeah, it's not free, but it's free for researchers. We can apply for a research account. Basically, that's free, yeah, for us. Yeah.
We have a question on Zoom. David, can you ask your question?
Hi, Yuxin. Thank you. I enjoyed your presentation. I just wondered if you have any interest in measuring or predicting nitrogen mineralization to get a better handle on some of the nitrogen recommendations in your RAM studies.
Yes, at least we need to include the organic matter information, I think. But I'm interested in doing that, but I need to work with someone with a lot of mineralization data, to predict that. I think by incorporating the organic matter information and soil landscape information, weather information using machine learning models, we can improve the prediction of mineralization, I think. Yeah, that will be interesting. And Solomon also discussed with me to use crop growth model to do the prediction. I think we can discuss, how we can work together to predict the mineralization. Thank you. That's an interesting topic.
We have another question on Zoom, Fabian.
Yes, hi, Yuxin. Thanks for the presentation. Not so much a question, but a follow-up to what David was asking, because as I saw some of those aerial images, and based on what I've seen also in my studies, that's one of the big challenges, I think, is determining the amount of, well, mineralized nitrogen, but also lost nitrogen. Those are kind of the two big pools that make our life difficult, right? We don't have a very good way to predict how much is being mineralized, and also depending on the season, some of that nitrogen that is mineralized is also lost. I don't know where that picture was taken, but it certainly looks like landscape position is also important. And so I would add to what David said in terms of mineralization. I think soil texture or soil position may be important variables as well to help us improve the site-specific management, because at least what I've seen with organic matter, it does help. I mean, over kind of a large area or large study, you see that the amount of organic matter is linearly related to mineralization. But then there are sites or soils that are pretty much the same, and they have substantially different amounts of potential mineralizable nitrogen, and we just don't really understand yet very well what is triggering those differences. So just, again, not a question, but a comment, a thought.
Yeah, so we need to try to estimate that, but the current approach is basically we just observe the crop growth conditions. That's an indicator or integrator, of all these processes, because it's really very difficult to predict all this, in a spatial and temporal resolution that's suitable for precision agriculture. So now we are taking a simpler approach to just let the crop tell us, but of course, based on this, we can continue to improve, to try to improve the